From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. Our guest today is Sam Naffziger, AMD's Senior Vice President, Corporate Fellow, and Product Technology Architect. He's been the lead innovator behind many of AMD's low-power features and chiplet architecture, and has spent the last 30 or so years designing processors at Hewlett-Packard, Intel, and AMD, and he has more than 130 patents, which is blows my mind. And this episode is brought to you by Mouser Electronics, a global authorized distributor offering the world's widest selection of the newest semiconductors and electronic components. So Sam, I'm thrilled for this chat. How did you get into tech? Did you always know you wanted to do engineering?
That's funny. So I went to school in the early 80s, high school, and we had a computer course that I took in 10th grade. We were using super primitive equipment, these old teletypes and the manual entry of the coding. And we upgraded to mini computer terminals after time. But I was just fascinated by that computer world. It was just like a magnet to me. And so I got in, I was staying after hours, programming and understanding the ins and outs, hacking different things. So yeah, I was immediately fascinated and drawn to computers and computer design, programming.
I don't think I've ever had anyone say they started on a teletype before. That's really fascinating to me. Do you remember transitioning over from a teletype to a computer? And do you remember what maybe the first terminals you were using, what those were?
Yeah, boy, I forget the name of the mini computer. Our terminals were called Super Brains, a funny name, but the after that course, I started reading up on computers and really got into the computer world. And the my first computer was this Radio Shack TRS-80. So nice. It was their little PC built on the Z80 microprocessor, and I spent my entire summer earnings painting houses to buy my own computer. And it was $1,200 back then in 1982 for one of these little things, but that was all I wanted with my money. And I bought I bought books on how to program in assembly code and got into the guts of the machine, understanding the architecture, and that's what I was doing on my lunch breaks on my painting job. While the other construction workers were hanging out, I was sitting there reading my programming book. I was definitely an odd duck to them. But I started out as a geek, I guess. Just couldn't help it.
That's wonderful. I love that picture of you like covered in paint, reading up on computer architecture. Yep. So you then, I assume, went to school for computers and computer stuff?
Well, yeah. So obviously my accomplishments there, and I got into some programming in high school and earned even a little money at that, and that helped me get the attention of the Caltech admissions crew and along with the usual academics. So went to Caltech and was in, I started the general, they do a very, rigorous science and physics and engineering program. And so I was doing a lot of the fundamentals of physics and electrical engineering. I got to take a course under Carver Mead there, who obviously one of the luminaries of computer and VLSI design, and really got excited about the VLSI design field. So circuits and computers. But it wasn't until I did my master's degree at Stanford that I really specialized in computer architecture, which was actually a great way to do it, in my opinion. I started at Hewlett-Packard after getting my bachelor's in more general electrical engineering at Caltech. And then after a couple years there, I entered they had this great honors co-op program where HP would fund and, pay for your time to go to a master's program if you met their qualifications. And so I got to go to Stanford there after kind of cutting my teeth on a bit of industry computer design. And I knew exactly what I wanted to do. So I was a lot more motivated to specialize in the computer architecture field, studying under Mark Horowitz there, Michael Flynn. And that's how I really got into the computer architecture space.
So, how did being in industry for a little bit change your perspective when you went back for your master's?
Yeah, well, it helped me understand what I really enjoyed, what was exciting to me. And that's how we do our best, achieve our potential, right? Is finding something that's just internally motivating and really fun to do. And I mean, just like back when I was in high school, computer architecture just was somehow something that was fascinating and still is to me. So then, at Hewlett Packard, they were just starting up they had started when I got there, the PA Risk design team to design their own RISC processor for workstations and computers, servers. And so I knew that was going on. It took a couple years for me to work my way into being a contributor on those designs, but that endeavor there also kind of got me focused on computer architecture, and so I got all the fundamentals there with the Stanford coursework, and really leveraged that. It was super applicable, great program. So yeah, it all kind of came together there.
Very cool. Can you just set the stage for us? Why does power matter? Like, who cares if my chip uses more power?
Yeah. Well, it matters on so many levels, right? So I guess I'll start with one of the most obvious, which is notebook processors and smartphones. Battery life is super critical on those. And I just was on vacation last week, on the plane a lot of hours, and I want my laptop to last. And so optimizing for battery life power is obviously very important and first order. But that's a lot different from, say, in the data center server space. And in the data center, we want to keep those things fully occupied. They're going 100% of the time. In our notebooks, we can turn things off between keystrokes as you're typing, and the idle percent time is 90 plus on those things. So it's all about low power modes, exploiting those idle periods to save power. In the server space, it's about getting your computes done with the least energy per operation. And that's a whole different focus area. And it's super important in the server space because, of course, these data centers consume megawatts. We just released the Frontier supercomputer built around AMD technology, which consumes, I'll probably get the number on between 20, around 20 megawatts, right? But that's a lot of megawatts. But we get over an exaflop of performance out of that. 10 to the 18th, I think it is. And so we're getting a lot more flops per watt. Even though the megawatts is high, we get a lot more flops out of every watt. And that's the key in the server space. And as you can imagine, if we were using yesterday's flops per watt metric, it would require over 100 megawatts to deliver that same level of exaflop performance. That's a whole nother power plant. And so that's kind of an obvious impact of power consumption there. So we've got to keep driving the power per operation down. Then there's the cooling overheads, and there's just the environmental impact, the carbon generation to provide those watts, the infrastructure, the expense, and all of it drives costs way up. And it means that we just can't grow the computes fast enough if we don't get the power down.
So I want to dig a little more into your time at HP. Working on those processors, was power a consideration you had to think about? And well, we won't get into the power stuff quite yet, but for HP, was power something they had to worry about?
Yeah, no, that's kind of fun to think back to our priorities then. And it's taken a long time for the industry to really internalize that power consumption and optimization as a first order limiter. And back then, it was definitely all about gigahertz and just raw performance. Actually, it was megahertz back then. My first processor was 65 megahertz. So, but yeah, it was more about that. In fact, we were looking into BiCMOS and all these high power technologies, and clock gating was kind of taboo actually, because people were afraid that by turning the clocks on and off, we would generate big transient events on the power delivery and cause failures and all this stuff. So there was a lot of concern, and it really was not a first order issue. And Understandably so. These were in the grand scheme very small designs, and so it wasn't until early 2000s that power became a first order concern and limiter. Back, when I was starting into the Itanium designs.
Can you tell me more about the Itanium, the 64-bit?
Yeah, so that's a long interview to get into all the history on that. The PA RISC stuff was great, and actually that's how I first got started really understanding computer design, the nuts and bolts of implementation of microarchitecture, and the first one that I played a significant role in was the PA 8000, and I worked on the out of order scheduler for that, which was a whole lot of fun. And back then the implementation approach was very low level. I mean, these were really small teams, less than 100 folks, and the number of transistors, was really small. We could handcraft the gates for the particular implementation of the microarchitecture that we were doing. So, and I actually did a lot of my own layout there. Today we get these libraries from third parties and feed them to tools. Back then, I was doing my own libraries, laying them out to make them small and tight, and placing each metal track so that the routes went where they were supposed to go. And we ended up with a super dense and optimized design, which was just great doing top to bottom like that. And that kind of low level engagement helps me today because I understand better just the fundamentals of the transistor implementation, wires and everything, and how it trades off with the architectural choices. But so that was PA RISC, and then as you're aware, I'm sure we HP at the time was starting to disaggregate their functions, and they at a management level decided that they would be better off letting Intel specialize in processors. HP focused on systems and software, and so they were engaged in this joint development with Intel on the Itanium, which they believed was the future of computer architecture and the next great thing. And so I got pulled into that after my PA RISC development work, and we started working on what was called the McKinley design, which was the second generation of the Itanium. The first one was Merced, which was headed out of Intel Santa Clara. So the Itanium was obviously completely different. It was an in-order execution. I'd been working on the out-of-order queue on PA 8000, so it had a whole new set of design constraints, and we dove right in, and then that's how I ended up at Intel, right? Is because then our whole microprocessor team got transitioned over.
Can you briefly explain the difference for those who don't know between in order and out of order?
Right. So out of order was a new thing, and with the PA 8000, we kind of led the industry in implementing an out of order execution engine. The traditional in order is very intuitive. You get a sequence of instructions that tell the computer what to do. Load such and such from memory, add these two numbers, write it back to memory. Straightforward things, and you just execute those through and do it as fast as you can. So, gigahertz is super important, and a whole bunch of other factors. Well, out of order says, well, a lot of these things have dependencies. Maybe your data is not in memory; it's further away, and so it takes a long time to load it, and then everything else is backed up, waiting for that data to come in. What an out of order design does is it enables looking ahead in the code stream and finding other work to do that isn't dependent on that slow thing and executing that out of order. And then when the slow thing comes back, it gets done, and then everything continues. But you do a lot more in parallel with out of order. And as you can imagine, it's complicated because if you do too many things early, then something can change when the slow thing shows up and the data is different than expected. So you need to be able to unroll your activities, and so you need history to track what you did, so you can back out of it if you did the wrong thing. And so it's actually quite complicated. And one of the premises of the Itanium architecture which was in order, but with a twist. The in order was a very long instruction word architecture where it had a lot of things that could, in theory, be done in parallel, and the compiler decided what would be done in parallel instead of the real-time processor itself looking at what could be done in parallel. And so that was a fundamentally different premise, was that we would push all this complexity on the compiler instead of having the hardware do it. And so it introduced a bunch of constraints. And the first of all, just say that premise ended up being incorrect, right? It was the real time, computer driven optimizations were just inherently more efficient. And we were able to manage the complexity and do those out of order designs in a very efficient way. And of course, that's what all today's designs are based on. But the Itanium took a detour and said, let's do it in order, have the compiler figure it out. And so that provided a whole new set of constraints on the machine design.
It's almost like in order is more of a physics problem, where out of order is more of a how clever can we be challenge.
Yeah, that's a good way to put it. Yeah, in order, in fact, well, first of all, as I mentioned before, in order, the best way to get performance is just run faster. Running faster and out of order helps too, but there's a lot of different dimensions. Branch prediction becomes super important because if you can predict branches accurately, then you can execute down that predicted path a long ways. And if you're correct, all that work is useful work. And so a lot of innovations in performance have come from branch prediction, for instance, and also prefetching to get the data in. Well, with out of order, it's mainly just about churning through your pre-selected set of instructions as fast as possible. And the other thing about in order is the dependencies on data to your local cache storage become super critical, because with an out of order design, you can hide those latencies by doing other work while you're waiting for the data to come back. With in order, if the data isn't there, you just got to wait, right? So I ended up doing a lot of innovative things in the cache system for the McKinley design on Itanium, and invented a way to do a single cycle L1 data cache, which was unheard of and still is, but it used some special tricks to pre-validate the lookup tables and everything, and use some other circuit stuff. But so that was kind of a fundamental key to getting as much performance as could be gotten from that. And then a very wide 4-ported L1D cache. I could go on. Oh, the other thing that's relevant is we also innovated on the what was called the L2 cache, really like an L3. We pulled on the original Itanium Merced design from the Intel team. They had these external memory chips to provide 4 megabytes of cache. Well, I worked with our team, and we figured out how to do a super dense cache design where we could pull 3 megabytes onto the die. So the same die size as the original Merced, but we crammed 3 megabytes of cache on there, much lower latency. It was lower power, but we didn't really care about power at the time. But it's interesting. A lot of the same guys who worked on that L3 cache are the ones who've contributed like to the V cache on our AMD processors today, actually, because they came over to AMD with me. But innovations in cache design have been super key, but they were more critical for that in order Itanium.
Okay. I could nerd out on this for the next hour, but I think we gotta move on to your time at AMD. How did that transition look from HP to Intel to AMD, and what did you learn through that process?
Yeah, no, that's a good one to think back on. I was excited to be at Intel, so HP had a lot of strengths. I really liked many aspects of the culture there. The HP way provided great, just a lot of foundational approaches to good management, to engaging the employees. I still have the 11 simple rules that Dave Packard had posted above my desk, because they're so important. Ways to recognize others, give appreciate, don't criticize, don't be negative. Really, fundamental good management practices. but also it was kind of this. It was more of a comfortable culture. Their motto was no one ever gets laid off. You kind of 8 to 5, and I was a little more ambitious. I really liked a more performance oriented, aggressive culture, and Intel had that culture. Certainly, AMD does in spades. So it was actually good. I enjoyed moving to the more hard driving, fast paced Intel and AMD culture. But the problem at Intel wasn't so much Intel; it was that I was the lead implementation architect for Itanium, and I could read the writing on the wall that there were fundamental architectural problems with this design, and that it was never going to be the flagship, most important processor that had been envisioned to be. And so I started looking around for other opportunities, right? Because that was what I was tagged with doing. I didn't want to be the captain of the Titanic, as some people termed that design. Um, So I had plenty of industry contacts from my engagements in conferences and such, and knew Bruce Gieske from AMD, and so I kept talking to him, and he and Dirk Meyer decided that they would make an investment in a design center in Fort Collins. So I worked with them, and they pulled me over, and I became the first employee here at the AMD Design Center in Fort Collins. And we got things started, and it was, obviously contingent upon that design center becoming a viable contributing part of the CPU team. But that didn't take long. Within a year, we were at over 100 really talented engineers from the area here. So worked out really well. Obviously, Intel wasn't too happy, but it was the right move to to bid adieu to Itanium.
Didn't want to go down with the chip.
Better things. That's right. Yeah.
Yeah, understood. So what did you start doing at AMD, and what about the program and the projects there got you excited?
Yeah, that was an interesting role. The careers take twists and turns. I think it's well recognized that the bulldozer design was not a roaring success either, but that's the design that was under development when I joined AMD. So I became part of the bulldozer development team, but I chose as my focus power optimization. And actually, yeah, I should roll back a little bit, because the way I got into power optimization was I was working on Itanium, and it became evident that the nature of this VLIW architecture was just inherently power intensive, because it's very wide, and you ended up doing a lot of redundant work, and it didn't have a lot of the real-time optimizations out of order could leverage. So I started studying this power problem. It's like, okay, we got to improve this architecture. And so I drove a lot of really leading edge power management approaches around adaptive techniques and adaptive clocking, low power circuit design. And we got the Itanium power way down. Of course, that wasn't enough to save it, but it did provide a lot of valuable learning. So I brought a lot of that institutional knowledge with me, and started evangelizing low power design on the AMD side. And it was still very much a fully performance oriented culture. It's like, every last bit of instruction per clock improvement, we got to get, the last few megahertz, which is all fine and good. But power also needed to become a first order consideration.
So did people look at you like you were crazy when you started talking about power and designing for low power versus performance?
Well, they would, people recognize, I wouldn't look at me like I was crazy, but at the end of the day, when push came to shove, it would always be deprioritized, because we never have enough engineers, resources to do things on the short schedule that management wants us to do them, right? So so people would say, oh yeah, power consumption is important. And I'd say, okay, I need 5 engineers to work with me to do all these optimizations. Like, oh, those guys are busy eking out megahertz on this other block, so.
So it wasn't a priority yet.
It wasn't a priority. So I had to be, creative and getting other power concerned people to work on stuff on their spare time, a lot of nights and weekend stuff, and prove out techniques and the value that they delivered, kind of, on the sly. And so it took time and a lot of evangelization, but there was a commitment at the top. The Chuck Moore and Bruce, they recognized that power was important. So it did start taking hold. And so that was a lot of the first focus for me, was getting power efficient approaches into the AMD culture. It took several years. And then inventing and implementing a number of power management capabilities. All the stuff you hear about now with Boost and adaptive clocking and all that. I started work; those were brand new in the early 2000s, and so I started developing those and getting them implemented in the design as kind of extra little things on the side that we would use in case they actually proved useful in silicon. And turns out they did, thankfully. And I remember the battles I had to fight to get a power management microcontroller implemented. And because that was a whole new thing, people were like, "Oh, we just use hard-coded state machines for this stuff. We don't need, it's way overkill. Firmware to manage power. A lot of opposition." Well, there was another engineer who we had this really tiny little microcontroller for other functions to manage the I/O interfaces. And so I managed to get a backdoor path into that microcontroller and some code space, so we could actually sneak in, so that the design leads didn't actually know we had this backdoor. So I didn't have to negotiate for an official aspect of the program. So we got this stuff in there, and it proved so valuable, and that flexibility and programmability on that design, that suddenly it became an essential element for all future processors. But a lot of stuff like that.
Well, now, 2022, it's hard just to find a power management IC in stock. So clearly it was the right move.
Yeah, no, we had to pull all that in, and it gives you the real-time adaptive responses and everything that are necessary. It's absolutely essential.
So taking a brief step back, what about technology today and about power and about IC design would surprise you if you could go back and show yourself when you were like 1990?
Well, everything was new and exciting in 1990. But, as I mentioned, we were handcrafting the gates and doing things on such a small scale. I absolutely could never have imagined the scope of the processors we're designing today. The billions of transistors, the level of parallelism we achieve, and the width of our execution engines. It would have been absolutely mind-boggling, and I would have been amazed. But and then the level of automation that we have. So, handcrafting gates is just not a thing anymore. And we had our bake-offs, and there was and there's still pockets of the industry where there is an entrenched desire to do a lot more low-level engineering, structured design, we call it, instead of feeding it to this automated synthesis place and route tools. But the level of automation would have been shocking to me as well. But it's absolutely essential. I remember that first out-of-order engine design I did. It was incredibly small and efficient and everything, but it was really hard to understand, and it wasn't transferable. And the poor engineers who had to pick it up and port it to the next generation, I was there was always, my designs were notorious for being a big challenge. It just wasn't scalable, right? So that's why the tool-based approach is so powerful, because we can do very complex designs that are scalable. Those.
Okay. And then touching back into power, and maybe now in the Zen architecture, what are the key factors when you look at optimizing for power?
Yeah, if it ended up working out super well, that I had been able to drive these low power approaches on a suboptimal architecture like Bulldozer, because that required a whole new set of methodologies and design awareness and power approaches. And so those were all ready in place then when we transitioned to Zen. And the team had gotten bought into the criticality of power optimization. How do you track it and optimize it? That's a fundamental of engineering, right? If whatever gets measured gets improved, right? And we now actually had approaches. We couldn't even really measure the power. When I started on Bulldozer, we didn't really know how much power we were going to consume. It required a lot of complex approaches to do that. We had all that in place, and we knew that power was going to be a first order priority. So I worked with the architects there, and we set some very clear goals for 5 watts at 3 gigahertz or whatever the power metric was, which was very aggressive at the time, but it was still achievable. And the team was bought into it, and we put the metrics in place to get there, and drove it, and ended up working out super well. And of course, we've generationally improved from there. But it was you got to lay the groundwork. You can't do that kind of a revolutionary power efficient design straight out of the gate. It has to be built on a set of methodologies and approaches that the team already understands. And so it actually was really good to have started early on the Bulldozer stuff.
So the iteration is really helpful. Can you talk to me about PPA, or power performance area? Kind of set the stage for me and the listeners.
Yeah, so those are the metrics. Yeah, power performance area optimization that's a condensation of what makes a processor valuable to the industry, right? So the obviously performance is essential, but it's performance within a fixed power envelope. So performance at any cost is not useful to the industry. It's got to be within the constraints of the power capabilities, the cooling capabilities of the design. So that's why we have P&P. And then area is fundamental, because more area, intuitively drives higher power, right? More area means you have more gates, your wires have to go longer distances. So that's not power efficient. It's also not performance efficient, because those distances take time to traverse. And so there's this virtuous cycle when you figure out how to make denser designs. And that means you have to be relentless about optimizing out unnecessary logic. Everything that goes in the design is actually contributing to performance. It's not just a legacy feature. Find a cheaper way to do that legacy stuff, or a slower way that isn't in your critical path. So yeah, PPA optimization is the fundamental target of every core design CPU and GPU and accelerator.
I understand you're also working on you have worked on some of that for GPUs as well. How does a GPU stack up against a CPU when you're looking at it from a power perspective?
Yeah, no, that was a really fun assignment I took on about 5 years ago. So I focused on the CPU power optimization, and that had gone really well with Zen. And our GPU power efficiency was lagging relative to the competition. That's well understood back in the graphics 8 and 9 generations. And so I joined the graphics team back in 2017 to go ahead and lead the PPA optimization efforts there, and went in knowing very little about GPU architecture. We had adopted some of the power management approaches into GPUs, which are kind of high level, but now I was going to dive into the guts and figure out how to leverage the CPU approaches to improve it. And that took quite a bit of time to get up to speed on the GPU capability. It's a highly parallel design, a very different set of constraints. But it turns out that the approaches are fundamentally transferable from CPU to GPU. There are schedulers in there. There's, of course, big math data paths, which CPUs have. There are caches. And so all of these common structures. The other thing that I had at my disposal, which was made the job much more efficient, was I could tap the CPU team that now really understood power methodologies, low power design, PPA optimizations, and get a chunk of their time to come in and work on the GPU stuff with me. And as I said, there was a lot of parallelism or parallel requirements in the GPUs. So it was fun to learn the constraints of the GPU and how the CPU approach is aligned, and and we just churned through it. And as you can see, the PPA of our GPUs has improved dramatically. And there was I should roll back too. I had to do quite a bit of the same sort of what you call evangelization of the importance of power to the GPU team as well, because that really wasn't part of their culture. And so, and that just, they were great, smart engineers. And so I distill it down to a few key metrics and say, hey, this is why it matters. Here's how we're going to track it. And as soon as you have those things in place, the team's motivated. They can see the progress they're making in reducing power with design iterations, and then they just churn through the work. And so that's come together well. And we now see, GPU design points are converging a lot more towards CPU in terms of frequency and area and everything else. So
it's an interesting parallel to see where the processor teams were super focused and hyper focused on performance, and you came in and kind of did some power evangelization, and then the same thing happened a decade later on the GPU side.
I know that was a great opportunity to have, and obviously it wouldn't have happened. Well, I would say the improvement rate was at least twice as fast on the GPU side, just because I had the CPU success there and the CPU team capabilities to tap into. Also, the obviously the full support from the AMD leadership team, and so it was super exciting to see those gains. I mean, I've talked about this a number of times, but our Navi 2 design, we pushed the frequency higher by 25%, while simultaneously reducing the power by 25%, which is a tough thing to do. But that's because the team just they rose to the challenge, and there was a lot of opportunity there. And the frequencies and low power, I mean, it just enabled us to hit much higher performance levels and performance per area, right? Because that's another thing on the PPA equation. You think, frequency is just performance, but it's actually performance per area. Because if we run at 1.5 gigahertz instead of 1 gigahertz, we're getting 50% more work done in the same design footprint, as long as you didn't grow it a lot. So pushing frequency has been a real focus there.
Have you watched or followed like the overclocking community at all? Is that of interest?
It's I do follow it some. It impacts our design constraints. We actually we do have to make design considerations to support the aggressive overclockers out there, right? Because that's an important part of our market base. And so yeah, we want to have a little design headroom. Obviously, we can't push the bleeding edge. It's an interesting balance, because part of what I've done to get our processors to go faster and better PPA is eliminate all of the extra margins we have, So I eliminate the voltage droop margins by adapting to it. We eliminate temperature margins by measuring the temperature and running it right up to the reliability limit, as much as we can, which means there's less there for the overclockers to extract. And so that has been an interesting balancing act to walk. But we provide them lots of tools, and there always is more margin there to get.
Surely. Yeah, it seems like there's so much a trade-off of reliability versus performance, and what's going to be the best for the users at large in the long term versus trying to get to the highest clock speed for 30 seconds, right?
Yeah, that's the right. There's sustained performance, and there's that instantaneous boost, and you want to be able to reward the overclockers with some benefits from their efforts, but that's always there with better cooling as well, because once again, that we can't have a infinitely expensive cooling solution. We have to balance the cost and performance, and so if they want to pay for something to keep the temperature a lot lower, that unlocks more capability in the part. And so what we've done is use our power management circuitry to recognize that we're at a lower temperature. We measure that real time, and then that enables the part to automatically run faster, for instance. So those are some of the capabilities we've put in.
So overclockers are always looking to pull, it almost feels like a future state of where processors could be. My question then is where is the future state of power? You're on record of saying there's an approaching power problem. Can you tell me more about that?
Yeah, well, as we mentioned, power is the first order limiter to how much performance we can deliver. And overclockers are willing to spend more power to get that last increment right. But that isn't a transferable capability. The entire world can't consume that level of power because it would um, overwhelm the power grid, right? So the problem, though, that we're facing is the diminishing returns issue. So it's been much discussed that the benefits of Moore's law scaling are significantly slowing down. And it's appropriate to be skeptical about such prognostications, right? The death of Moore's law has been prophesied, many times over the decades. And in fact, I was fully convinced by this detailed paper I read in the like the mid 2000s on that 22 nanometer was going to be the last node that could really achieve good scaling, because we were going to require three-dimensional devices after that, exotic gate oxide materials, and all these other things. Well, with a few $1 billion of R&D investment, those problems were resolved, and we've had a lot of great scaling since the 22 nanometer node. But now we can just look at it from an empirical sense. It's no longer a forward-looking statement. It's an observation of the present that node introductions are slowing down. They are not delivering as much as they used to. And the other thing we're hitting is, I talked about the great things in power management that the industry has accomplished and that we've done at AMD. And we have been squeezing more and more out of each transistor and out of each joule of energy we consume. We get a lot more work done. We are hitting the point of diminishing returns there as well. So the Moore's law slowdown definitely reduces the energy improvements generationally, and our power management approaches have done great things, but the opportunities are more limited going forward. And the compute demand is just exploding right now. So it's not like we've saturated the appetite for more computes in the world. It's actually only accelerated. The benefits to our daily lives from not only supercomputers solving for drug solutions and climate issues, but our navigational tools and speech translation and all those things all require a ton of compute. So this just is driving the power consumption up. We can't improve at the rate we used to based on the fundamental physics. The demands are going higher, so we definitely have a power problem that we're facing. Well, it means there are opportunities to find new solutions, and it's going to drive a lot more innovation, but the approaches of yesterday aren't going to suffice.
So that's kind of my question then, is like, do we just kind of throw our hands in the air and say, well, that's kind of it? Or what areas look interesting and have promise for the future to keep getting these types of improvements we've come to expect?
It's going to be a variety of solutions coming together, right? There's no single silver bullet here. And it's really, there's kind of an analogy to how we've managed to eke out so much improvement in the silicon front over the years, just through sheer determination and great engineering and investment. And on the power front, it's going to be a similar thing. Yeah, if we just rely on the approaches of yesterday, the power per processor is going to go through the roof, and cooling that is going to become extremely difficult. Delivering the power just at the processor level, with the currents going up to hundreds of amps, is going to be extremely hard. And then the density and the data centers, everything, it becomes impossible, right? So we will find solutions because we have to. And it's going to come from a bunch of approaches, optimizing at the system level, continuing our optimizations for power and power management. The technology will continue to deliver some, but it's going to be more on the way we integrate these devices. So we need to continue pulling things in from the system to the silicon, because that's intrinsically, the miniaturization is power efficient. But we also are going to have to be more flexible in the way we integrate those things. And that's where the bridge to modular chiplet architectures comes in, because the design architectures that are power efficient are going to be more and more domain specific. General purpose CPUs and GPUs, they've been a great ride. They're going to continue to be critical, but they just aren't that efficient for specialized tasks. And so for certain types of computation, for machine learning approaches, for a bunch of other, video processing, all kinds of audio stuff, things that we use our computers for, they're much more efficient run on an accelerator that is designed to just do those tasks well. But customers, applications, different data centers want different mixes of those capabilities. So that's where we need to be able to mix and match accelerators that are super efficient in different ratios, different proportions, based upon the need for the application.
So efficiency seems to be a pretty big topic then. Can you tell me a little bit about the 30x25 initiative?
Yeah. Okay. So recognizing that the challenges of improving power efficiency are even greater today than they were just 5 or 10 years ago, we wanted to set for ourselves and the industry a very aggressive goal that would actually accelerate the gains of the last 5 years when applied to the next five, which is obviously going to be extremely difficult because the basics of scaling are not in our favor. So the 30 by 25 accelerates the last 5 years pace by over a factor of two, which was just was a 12x gain. Now, 12x gains in any other industry would be amazing, right? in efficiency. Yeah. But in the computer industry, we have our sights much higher, and so we wanted to go, take it from 12 in the last 5 years up to 30x for some of the fundamental metrics and floating point computations for machine learning and for high performance computing. Now, how we're going to get there, we still, it's going to take invention, but that's the name of the game in our industry, is finding new approaches to solve these challenging problems. So it's going to be a system level design problem. And so that's why we framed the goal at more of a system level, a node level, not just a single processor, because we know that the silicon itself isn't going to hit 30x, right? But it's how we connect that silicon up, how we connect it to memory, how we implement the algorithms that it's going to be running. And so there's a software hardware co-design aspect, there's system design, there is the fundamental silicon architecture.
It almost parallels back to, we were talking in order versus out of order, where we had a physics problem and now we realize physics is maybe not the answer. We have to be more clever with what we're doing.
Yeah. And that's where we've gotten, away. We're transitioning from a hardware centric approach in the processor community to much more I would say it's a multidisciplinary approach. The packaging teams and engineers are first order participants in the process, and then the software engineers as well, because it's the software guys who are generating the code that everybody runs and how they actually experience the computer, right? And so we've started a whole new level of triaging the commonly used libraries and loops and everything else, understanding how that implements on our hardware. And then we are designing our hardware to execute that software much more efficiently. So it's a fascinating new level of optimization.
I want to dig into packaging a little more because that whole technology space fascinates me. But when I was reading up on this, one thing caught my eye. Normally, when I see a list of supercomputers, it's by number of cores or most powerful. But I understand there's a green 500 list of supercomputers. Can you tell me a little bit about that?
Yeah, so the top 500, and this was, I don't know how many, 10 years ago or so, they started tracking the most power efficient supercomputers, which is simple. So there's this high performance LINPACK metric, which is the matrix multiply kernel for a lot of commonly used HPC code. And it's that flop rate that is used to say who's at the top performance list, right? So the top 500. But then they started to divide that flop rate by the number of watts used to generate that number of flops. And so you get a performance per watt metric out of it. And arguably the performance per watt is more important than the raw performance, because we're all limited by power consumption going forward. So if we don't improve on that performance per watt metric, performance doesn't go up either. It doesn't matter how good your theoretical performance is. If you can't power the thing, it's it's not helping. So Green 500 tracks that performance per watt. And that's what I was so proud of on the Frontier deployment was we did a run on the top 4 spots of the Green 500 with this MI 250 implementation and plus Epic design. And that's just the system level power consumption. So it includes the CPUs that do the organization, the work distribution, or GPUs, number crunching, and all the overhead, and then dividing that by the number of flops that actually come out. So we were over 2x, 2.5x the
Wow,
prior occupants of that list. So it was very good.
that's quite a jump. 2x power, power efficiency.
Power efficiency, yeah. Yeah, well, we got to keep that improvement rate up to hit 30x, right? So
Yeah, fair enough. Your work cut out for you. So one of the areas you're looking at to make those improvements is in the packaging space. What's your background with packaging? Well, let's start with what is packaging and what's your experience with it?
yeah, no, that's good. Well, it's kind of gets to a funny story. We talked about when I joined Hewlett Packard long ago. I was originally slated to start on a circuit design team. We're designing chips for their computer systems, but there was some horse trading that went on, and I ended up on the package team when I first started. And I was kind of bummed. It's like, so I'm working on this advanced packaging development, which was advanced back then, not by today's standards. But I decided I'll roll up my sleeves and understand, and dig in and make a contribution. And I learned a lot through that effort and how to analyze, model, and packaging manufacturing flows. And I flew out to manufacturing facilities, and so I was really early in my career. And then as soon as I got a chance, I jumped over into CPU design, of course, which I love doing. But that package background that I was forced to engage in actually proved very useful. And as time went on, 20 years in, I began to realize that packaging, which back to part of your question there, packaging is the way we interface these tiny little silicon chips to the rest of the world. So the little wimpy electrical signals that these silicon devices can generate, they have to make it onto a motherboard and then to something like our displays, and they have to receive inputs from the keyboard. And the packaging is how all that stuff connects in. And it ends up being extremely complicated. And it's gotten even more so as we've been getting to larger and larger chips. They consume a lot more power. And now we've been moving into this chiplet domain for a whole bunch of reasons, where packaging is a first order technology consideration.
What is a chiplet?
So you'll get differing definitions in the industry. The way I like to define a chiplet design is when we take what is a monolithic system on a chip, or SoC we call them, and as an industry we've been growing these SoCs over time. So 100 millimeters squared to 200, 400. Some of the biggest designs today, 800 millimeters squared, which is as big as a manufacturing facility can actually print a chip. And those big chips have low yield. They are inflexible, right? So you've got this chip and it can just do one thing and it'll do it well. But as I mentioned, we need more flexibility in our computes now because we have to do a whole bunch of different things in a mix and match approach to get the efficiencies. Well, what a chiplet design is it takes what would have been a big monolithic SoC and it disaggregates it into components. And any one of those chiplet components is not a product in and of itself. It's just a piece of a larger SoC. So that's my preferred definition for a chiplet. And our Rome server design is a great example of that. So the server architectures had been in the monolithic SoC approach for many, many years, growing bigger and bigger and more cores and more cache. And what we did with Rome is we said, you know what, we want to take advantage of the most advanced manufacturing technology, 7 nanometer, super complex, very expensive to manufacture. We can't afford a gigantic chip because it's not sufficiently flexible, too expensive. And so what we'll do is we'll split what would have been a monolithic SoC into the interface components and the CPU components. And we'll just put the CPU in 7 nanometer as a very small, high-yielding chiplet. And we'll be able to tile many of these, up to 8 of these little CPU chiplets around the big interface die. So those
Huh.
CPU chiplets are, they can't be productized. They're just a component of a chiplet SoC. The I/O interface needs the CPUs to do anything useful as well, right? So that's a chiplet design, and it solves a whole bunch of problems for us. It enabled us to get to a very high core count by stamping out a whole bunch of these high yielding small 7 nanometer chiplets. It also enabled us to use a cheaper legacy technology for the big memory interfaces and all the stuff that talks off chip. So we could optimize costs, we could optimize power by being in 7 nanometer, and we could get to a virtual SoC that was bigger than anything that could be printed with a monolithic.
Yeah, I have friends at who have worked at large server companies that I won't name, but I can picture, they're in the on the wall behind them. They have these big old chips, but being able to split that up seems like it would have a lot of advantages.
It has huge advantages. So it obviously, it enables configurability for one. So we could have low core count servers that had only a few CPU chiplets. We could have very high core count servers. And we also took those same CPU chiplets and put them into our desktop processors. We only use 1 or 2 of them there, and it got a different I/O die that has a different set of interfaces. So
Hmm.
we were able to use this single chiplet into multiple markets in configurable counts and formats. So it was equivalent to like 10 different SoCs at the end of the day, what we ended up productizing out of just 3 chiplets. One I/O die for our desktop, one for server, and then the CPU itself. And where the industry is going in the future is, what about having something other than just a CPU chiplet? We can put accelerator chiplets in there. We can put all kinds of new functionality and mix and match for a market.
Yeah, it's almost like going back to discrete ICs, but inside of a bigger, SoC type system.
I know the industry goes in these cycles, right? I know it was all about integration for so many years for very good reasons, but now we're taking the architecture of an integrated design, but then using advanced packaging and interfaces to disaggregate it.
So how have you seen packaging grow? Are there any moments or capabilities or advancements that have really surprised you or caught your eye in the last decade or so?
Well, I'd say just being able to pull off that Rome, 9 die multi-chip module was great. There was a lot of concern. There was a lot of opposition to taking that risk because it required advances in test capabilities, right? So if you're going to put down 9 chips on a package and require all of them to work, your test capabilities need to be very, very high quality to ensure you put down good chips. So that was a big challenge. So just being able to do that has been exciting. Now, as we go forward, we are investing in working with our partners and suppliers on much more fine pitch, lower power interface approaches, right? So, there's a tension in power consumption and chiplet design because it's intuitively higher power to talk between chips than just keeping those little wires on your tiny silicon, right? So we've been investing a ton of engineering in the industry as well in optimizing those chiplet interfaces, and that's been highly valuable. Then the culmination, I think, of the chiplet approach is the 3D stacking, and that's what's been probably the most exciting development in my career. Is we've actually been able to productize the industry's first, high performance 3D stacked processor with our what we call our V-cache stacked on top of the CPU compute die. And to see that actually work and yield is exciting.
How do you so it's 3D meaning you basically are sandwiching wafers on top of each other, right? Like how does those connect? How does that work?
Yeah, it's a very sophisticated approach, and it's taken that was over 5 years in development to actually get that to market. And there are all kinds of steps that need to be optimized out. So yes, it's a it's actually a chemical bond. So they use a clean room process, polish down the wafers, expose the silicon dioxide bonds of the CPU die, and then take the cache die, similarly polished and exposed, and bond them together at the right temperature. And those silicon dioxide chemical bonds mate, and they generate a monolithic, essentially a monolithic chemical bond, glass-like structure. So it's extremely rigid. But then the trick is that embedded within that silicon dioxide are these copper pillars. And you heat those up to the right temperature, they expand, and they generate a metallurgical bond. So then you get the electrical connection on top of the mechanical connection. And those copper pillars can be patterned at a very tight pitch. And our designs use a 9 micron copper pitch called a through silicon via pitch, which obviously is, today's best C4 bumps for packaging are 110 to 130 microns, right?
Yeah.
So you take
nine.
the square,
You said 9?
yeah,
That's
9
wild.
micron. So the density is, of course, the ratio of the square of those numbers, right? So 100 times more dense, and a very low electrical resistance path, because these things are thinned down to 10 microns as well. So the density of interconnect is amazing, and so we can drive high bandwidth. It doesn't take any power to do that. It's just like driving across a chip, and we can put together diverse pieces of design in that way.
That's incredible. Well, when you look at these chiplet designs, if I'm just looking at like a motherboard, for example, does it look like one package, or will it look like multiple chips kind of spread out? What will I see?
Yeah, I mean, you'll just see one package.
Okay.
The way the typical users see it, we have to have a heat sink or a heat spreader on top, and so we glue those things or use indium or some other material to make the thermal connection, and that's all the user sees. So it looks like a single piece of design. And as we get to more advanced package technologies, those are like 100 microns or less, 50 microns apart. And so it's just this nearly invisible little seam between the chips, and they talk over these high density interconnects. So obviously it introduces another dimension to our floor planning. And if we're going to have modular designs, those chiplets are going to have to conform to specific aspect ratios and areas so they can plug into the same spot, and their interfaces need to be aligned. And so a lot of fun jigsaw puzzle or Lego challenges to put these things together. But it does, at the end of the day, look the same.
Yeah. So do you have just like a ton of SerDes engineers then trying to get all these talking to each other well?
Well, what we want is to have standardized interfaces, and there have been good progress in the industry on things like the UCIe interface standard, Universal Chiplet Interface Express, I think it's called, but where the industry standardizes on one design approach. So that's one of the challenges with engineering. Everybody wants to optimize for their particular problem. It's a little different than the other problem, and so you end up with 10 different solutions. But with a bit of effort, we can work on standardizing to one, so we don't have an explosion in SerDes designers, which we can't afford. So we're making good progress there to get to standard interfaces that meet the power, latency, and performance, PPA requirements. But all that takes time. It's a new, it's a new field for the industry.
Wonderful. For for the people who are watching that are students or like early mid-career and are interested in learning more about this and getting into it, what topics should they study and what areas should they explore?
Yeah, kind of as you asked about the power problem and what are the solutions there, it's really an all disciplines space. And so there's going to be opportunities at all levels in the computer design, whether it's how to architect a more efficient accelerator that gets the most out of each joule of energy to solve a particular problem. The software optimization piece is huge. The packaging design, it's a very deep physics-based space, metallurgy and thermal mechanical effects, all kinds of detailed things. And critical advances are going to be required there. So that's a burgeoning field. There are the fundamentals of silicon scaling. Silicon's going to continue to scale. We're going to get process node advances, and they matter a huge amount. And so we need engineers working on that space as well. And then there's the overall the computer architecture, and it's an exciting time in that field as well, because we've got to integrate these accelerators seamlessly and efficiently, and whoever does that best and learns how to make a modular design act just like a monolithic design most efficiently is going to win. So yeah, many different disciplines working together. It's an exciting time.
So who would have thought that the packaging folks would have such an impact on how things play out for the future? Do you bring them in for planning and that sort of thing?
Yeah, well, that's what's been fascinating here at this stage in my career. Really going back to the packaging roots that I started out on, and I never would have expected that those skills would be so directly applicable to computer architecture. And so what we've ended up doing in our early concept exploration and design architecture generation is pull in all the different disciplines. We bring in the software team, we bring in, of course, the computer architects, the silicon implementation folks, and also now first seat at the table are the package engineers, because the capabilities that they are developing and they foresee being available when we actually productize this chip or this design are have a first order impact on how we architect it. If the pitches, the 3D stacking capability, the interfaces are going to support a certain level of bandwidth and power efficiency, it completely changes how we do the cache architecture, for instance, how we interface to memory, or how many compute units we can fit on the die. And so the packaging capabilities have a first order influence on how we architect the chip and its fundamental capabilities. And I never would have expected that. And, the deep sciences of metallurgy and, the thermal mechanical architectures would be impacting our computers.
Yeah, it's incredible how everything starts to matter when we get to this level of technology.
And that's how we determine who's how the industry is going to sort out the winners and losers, right? The ones who can succeed at this multidisciplinary task across software, packaging, silicon, and logic architecture are the ones who are going to win and deliver the most power, performance, and area efficient solution. But it's going to take all disciplines.
Fantastic. Yeah, absolutely. So as we wrap up on time, we like to do a bit of a lightning round, ask some kind of off the cuff questions. So you went to Caltech. I know that Caltech is famous for elaborate pranks. Are there any of those you were involved in that you can admit to?
It was a really fun culture to be a part of. Definitely, a lot. People loved science, and they also like to let some steam off. And the prank that I was a part of was the one in 1987. I think it was. We figured out how to change the Hollywood sign to read Caltech. I don't know if you remember that one, but it was it required a bit of obviously some great engineering of doing precision cutting plastics in white and black to drape over the letters, but also it was physically challenging because those Hollywood letters are over 50 feet high and they're on a hillside in the middle of brush. They have barbed wire on them. So we got all the precise lettering stuff cut and rolled. We divided up into teams and had to go, in the wee hours of the morning, sneak in there. And I was into rock climbing at the time, so we used my rock climbing equipment to ensure that we didn't lose anybody in the process, and scaled those letters and draped things down. And yeah, that got quite a bit of press. It was a lot of fun.
That's a big one. That's a pretty famous one.
Yeah, I was on the W to E conversion team.
So we recently ran an article in All About Circuits about chip art hidden in the silicon or in the chips. Do you have any experience putting your own little signature mark in there, or having your teams hide some little Easter eggs on the chips?
Those were the fun days. We could do things that aren't allowed by today's manufacturing design rules. But yeah, we could sneak those in the past and leave floating layers of metal and vias to draw designs. I think the most impressive one I was a part of was a Rolex watch. So we designed our first. But we integrated the floating point unit way back in the early 90s, which was a really big deal. We used to have a separate chip for that. And of course, maybe we'll go back to separate chips with chiplet designs. But we pulled that in, we called it Timex, and then I was involved in the architecture for the one that we called Rolex, which was in the PA8000. And we had a blank spot on there, and one of the bright young engineers wrote a script to digitize a picture of a Rolex watch and put that down. So if you look out there, I think that's on some of the photos of the chip art. But it was super cool.
Are there any out there that you think people haven't found yet?
Well, there are a few little ones, and I did put some in myself. But depending on what metal layer they're at and everything, they can be really hard to see. So yes, there are some more out there.
Okay. Yeah. If you could start a new career tomorrow and you couldn't do technology, what do you think you would do? Maybe rock climbing guiding?
Yeah, no, I do love the outdoors. I mean, being out of technology is hard to envision. So, but jumping in, I love the outdoors. I could see getting into like wildlife biology. Living in Colorado, we get outside, hiking, biking. Also fascinated by cosmology and the nature of the universe, and so maybe into some area like that. Definitely, science oriented is where I gravitate to. So.
Yeah, it seems like this is a natural fit for you for sure. From in painter's clothes, reading code on your lunch break to designing the next gen.
Yeah, I wasn't going to be a painter for my career.
Well, this has been great. Thank you so much.
Thanks for having me. This has been a blast to talk about technology and career and what matters in today's computer field. So yeah, really great to be here. Thank you.
That was Sam Naffziger, Senior Vice President, Corporate Fellow, and Product Technology Architect at AMD. Thanks again to Mouser for sponsoring this episode. If you enjoy this podcast, make sure you're subscribed in your favorite podcast delivery tool, and it would really help us out if you would share this episode on social media. So go check out the Moore's Lobby and All About Circuits social pages and share this podcast. Thank you for joining me today in the lobby. I'm Daniel Bogdanoff, and I'll be right back here in 2 weeks with Dr. Wei Li, Intel's Vice President and General Manager for Artificial Intelligence and Analytics.